Hey guys, welcome to this session on Spark tutorial. So let's quickly have a look at the agenda. We'll start off by understanding what is big data, and then we'll comprehensively learn about Spark. After that, we'll see how do Spark and Hadoop work together. Following which, we'll look at the Spark architecture, then we'll understand what are Spark RDDs and implement a demo with them. Going ahead, we'll look at the different Spark components, and then we'll implement a demo, each with Spark data frame and MLlib. And finally, there'll be a quiz to recap whatever we've learned in today's session. So let's understand what exactly is big data. To start off, let me ask a very simple question. What do you understand by the term data? Well, it's just collection of raw facts and figures, isn't it? So my next question would be, what is big data? So big data is a term that describes a large volume of data, both structured and unstructured, that inundates a business on a day-to-day basis. But it's not the amount of data that's important. It's what organizations do with the data that matters. So as we see over here, the amount of data being generated every single minute is very huge. So in just 1 minute, we generate around 98,000 tweets, send around 168 million emails, and create 1820 terabytes of data. Now that is a whopping amount of data being generated in just 1 minute. And in order to make sense out of this overwhelming amount of data, it is often broken down using 5 V's: velocity, volume, value, variety, and veracity. So volume basically refers to the incredible amounts of data generated each second from social media, cell phones, credit cards, M2M sensors, and so on. Then we have velocity, which basically refers to the speed at which new data is generated and also the speed at which this data moves around. Now, this data is generated from multiple sources and is present in multiple formats. So we have structured data, semi-structured data, and unstructured data. And this is the variety in data that we're talking about. So when we are dealing with this huge amounts of data, it is not possible that all of the data is going to be 100% correct. So veracity basically refers to the quality or trustworthiness of the data. Now, having endless amount of data is one thing, but unless it can be turned into something of value, it is useless. So this is why value becomes one of the most important aspect of big data. So those were the 5 V's of big data. Now, there are also a lot of issues which come along with this big data. So let's look at some of them. As big data increases in size and the web of connected device explodes, it exposes more of our data to potential security breaches. And many organizations have already struggled with data management and security even before the complexities added by big data. So many of them are drowning to keep up. Also, the more data an organization has, the more complex the problems of storing it arises, which in turn increases their overall cost. Also, processing this huge amount of data is not easy and consumes up a lot of time. So this is where we needed big data processing tools to deal with this huge amount of data. So we have Hadoop for batch processing of data and Spark for real-time processing of data. So now let's see how do these two differ. So batch processing is an efficient way of processing high volumes of data such as a group of transactions which is collected over a period of time. Hadoop focuses on batch processing, but as you can see over here, there is a time lag in processing this data. So the data which is generated on day 1 is processed on day 2. Similarly, the data which is generated on day 2 is processed on day 3. And on the other hand, real-time processing involves a continual input, process, and output of data. So it provides an organization the ability to take immediate action in times when acting within seconds or minutes is significant. So Spark helps in achieving this real-time processing. So again, as we can see over here in this figure, the data which is generated on day 1 is processed on day 1 itself, and there is no time lag in processing. So that's the major difference between Hadoop and Spark. So now let us understand about Spark briefly. So Spark is a cluster computing framework for real-time processing. It was Hadoop sub-project introduced in the UC Berkeley R&D lab in the year 2009, and it became open source in 2010. And in 2013, it was donated to Apache Software Foundation. So Spark provides an interface for programming multiple clusters with implicit data parallelism and fault tolerance. So now that we know what is Spark, let's actually have a look at some of its features. So Spark is real time. That is, it provides real-time computation and low latency because of in-memory computation. And Spark is also 100 times faster for large-scale data processing. And Spark is also polyglot. That is, you can write Spark applications in multiple languages such as Java, Scala, Python, R, and SQL. Spark also has a simple programming layer which provides powerful caching and disk persistence capabilities. And Spark also has multiple deployment modes, so it can be deployed through Mesos, Hadoop via Yarn, or Spark's own cluster manager. So now, let us look at some domain scenarios of Spark. So from small startups to Fortune 500s, almost every single company is adopting Apache Spark to build, scale, and innovate their big data applications. So let us see some industries where Spark is used widely these days. So industries like healthcare, media, finance, e-commerce, and travel are extensively using Spark to add value to their business. So now let's understand how are Hadoop and Spark used together. So Hadoop alone provided limited predictive capabilities as organizations were finding it difficult to predict customer needs and emerging market requirements. But with a combination of Hadoop and Spark, companies can now process billions of events every day at an analytical speed of 40 milliseconds per event. Companies can also enhance their storage and processing capabilities by working together with Hadoop and Spark to reduce costs by almost 40%. And by deploying a big data platform in the cloud, organizations can avoid duplication by unifying clusters into one, which basically supports both Hadoop and Spark. So now many organizations are already using Hadoop and Spark together. Yahoo, Amazon, NASA, and eBay run Apache Spark inside their Hadoop clusters. Hortonworks and Cloudera Hadoop distributions come bundled with Apache Spark. Altiscale uses Spark on Hadoop to provide big data as a cloud service. And Uber also uses Spark and Hadoop together to optimize customer experience. So now let us have a look at some of Spark's APIs. So Apache Spark codes can be written in Scala, Java, Python, and R, and we can also write SQL queries with Spark. But the most preferred language along with Spark is Scala. So let's have a look at some of the features of Scala. So Scala provides scalability on Java Virtual Machine, and its performance is also really high when compared to others. Scala also provides excellent built-in concurrency support and libraries. And well, a single line of code in Scala can replace 20 to 25 lines of Java code. And Spark is also extremely fast and efficient. So now it's time to have a look at Spark's architecture. So Apache Spark has a well-defined layered architecture where all the Spark components and layers are loosely coupled. So Spark basically uses a master worker architecture, and in the master node you have the driver program which drives your application. Now you might be wondering, what is a driver program? So basically the code that you're writing behaves as a driver program, or if you're using the interactive shell, the shell will act as the driver program. Now the driver program runs the main function of the application, and it is the very place where the Spark context is created. So assume that the Spark context is a gateway to all the Spark functionalities. So Spark driver and Spark context take care of the job execution within the cluster. Now Spark context also works along with the cluster manager to manage various jobs, and cluster manager is responsible for acquiring resources on the Spark cluster and allocating them to a Spark job. Now this job is split into multiple tasks which are distributed over the worker node. So these worker nodes are the slave nodes whose job is to basically execute the task and return the result to the Spark context. Then we have the executor, which is a distributed agent responsible for the execution of tasks. So every Spark application has its own executor process, and these executors usually run for the entire lifetime of a Spark application. So in a nutshell, the Spark context takes the job, breaks the job in tasks, and distributes them to the worker nodes. These tasks work on the partition RDD, perform operations, collect the results, and return to the main Spark context. Now, if you actually increase the number of worker nodes, then you can divide the jobs into more partitions and execute them parallelly over multiple systems, and it'll be a lot faster. And with the increase in the number of workers, memory size will also increase and you can cache the jobs to execute it faster. So now let us see the various ways by which Spark can be deployed. The system currently supports these cluster managers. So we have Spark standalone cluster, which is a simple cluster manager included with Spark that makes it easy to set up a cluster. Then we have Apache Mesos, which is a general cluster manager that can also run Hadoop MapReduce and service applications. After that, we have Hadoop via Yarn, and we can also deploy it with Kubernetes, which is an open source system for automating deployment, scaling, and management of containerized applications. And Spark currently supports these three shells. We have Spark Shell with Scala support, PySpark with Python support, and Spark R with R support. Now it's time to understand about RDDs in Spark. So when it comes to processing the data over multiple jobs, we need to reuse and share the data, which can be achieved through in-memory data sharing, which is actually a lot faster than network and disk sharing. And RDDs help in achieving this in-memory data sharing. So RDD stands for Resilient Distributed Dataset, and it is the fundamental data structure of Apache Spark. So by resilient, I mean fault tolerant, as it can recompute missing or damaged partitions in case of a node failure with the help of RDD lineage graph. And it is distributed since data resides on multiple nodes. And dataset basically represents records of the data you work with. So the user can load the dataset externally, which can either be JSON file, CSV file, text file, or a database. So now let's actually implement a demo on RDDs. So we'll start off by understanding how can we create RDDs. So there are three ways to create an RDD in Spark. So the first way would be to parallelize already existing collection in a driver program. The second way would be to refer a dataset in an external storage system. And the third way would be to create an RDD from already existing RDDs. So let's create an RDD by parallelizing a collection. So this would be the syntax for that. So first we'll create a collection, and this collection is a list which contains these three elements: Spark, Scala, and Hadoop. And then we'll use sc.parallelize to parallelize this collection, and we'll store this result in my first RDD. So this is one of the ways by which we can create a Spark RDD. The second way was to reference a data set in an external storage system. So let's do that. So I'll just type in val and then give a name to the object, which would be, let's say, text RDD, and then let me load this external data file. So the command would be sc.text file, and then I will give in the path. Right, so this was the second way to create our RDD. And the third way to create RDD is to transform an existing RDD. So we'll do that using the filter function. Right, so over here we already have an RDD which is text RDD, and on top of that RDD I am using this filter function, and I will be extracting only those elements where it contains the string Spark, and I will assign to this result new RDD. So these are the three ways by which we can create RDDs in Spark. So now that we know how to create RDDs in Spark, let's go ahead and perform some operations. So the first set of operations would be the transformation tasks. So these Spark transformations basically produce new RDDs from the existing RDDs. So it takes RDD as input and processes one or more RDD as an output. and each time it creates a new RDD whenever we apply any new transformation. So the first set of transformation function would be the map function. So this map function iterates over every line in RDD and it splits it into a new RDD. So using the map transformation, we can take in any function and that function is applied to every single element of RDD. So what I'll do is I will go ahead and create an RDD with the name X, and this RDD is made by parallelizing this collection. Now what I want is, using the map function, I want to add the number 1 to each of these existing element. So this would be the command for that. So on top of this RDD X, I'll apply the map function, and this will take in every single element and add 1 to that element. I'll hit enter. Now let me just type in y dot collect and let's see what is the final result. So over here we see that these were the initial values, and after applying the map function on top of this, 1 has been added to each of the individual element. So initially it was just Spark. After using the map function, it became Spark1. Initially it was just RDD. After using the map function, it became RDD1. So this is how we can use the map function. So now we'll go ahead and work with the flat map function. So with the help of flat map function, to each input element, we can have many elements in an output RDD. So the key difference between map and flat map is that map returns only one element, while flat map can return a list of elements. So over here, what I'm doing is, I have a list 1, 2 and 3. And what I want to do is, I want to duplicate each of the individual element 3 times from this RDD. So I'll use the flat map function and I'll take this element and I want to duplicate each of the element 3 times. I'll hit enter and let's see what do we get. So this was our initial RDD, and after applying the flat map operation, we see that each element has been printed 3 times. Now let's say instead of 3 times, I only wanted to duplicate it 2 times. So what I'll do is I'll remove this X, I'll remove comma over here. Now I'll hit enter. So see that we have duplicated this initial RDD like this. So the duplication is twice over here. So after this we have the filter function. So the Spark RDD filter function returns a new RDD containing only the elements that meet a predicate. So it basically narrows operations because it does not shuffle data from one partition to many partitions. So I'll go ahead and create an RDD which contains the first 10 numbers. Now from this RDD, I would only want the even numbers. So to do that, I can use the filter function. So on top of this numbers RDD, I'll apply the filter function and I will extract only those elements where the remainder is equal to 0, and then I'll collect the result. So this was our initial RDD, and after applying the filter function, we have extracted only the even elements. So the next function is intersection. So when we apply the intersection function on two RDDs, we will get only the common elements between the two RDDs. And the key rule of this function is that the two RDDs should be of the same type. So I will go ahead and create two RDDs. Right, so first I am creating an RDD with the elements 1 to 9. After that I am creating another RDD with the elements 5 to 15. Now what I'll do is I will apply the intersection function between these two RDDs and let's see what do we get. So we see that we have only the common elements from these two RDDs. So the common elements are 5, 6, 7, 8, 9. So these were some of the transformation functions. Now after that we also have something known as actions. So while transformations create RDDs from each other, but when we want to work with the actual data set, at that point action is required. So when the action is triggered after the result, new RDD is not formed like transformation. Thus actions are Spark RDD operations that give non-RDD values. So the values of action are stored to drivers or to the external storage system. So this basically brings in laziness of RDD into motion. So now let's work with the first action task, which would be reduce. So the reduce function takes the two elements as input from the RDD and then produces the output of the same type as it of the input elements. So let's say I create an RDD for the elements 1 to 10. Now what I want is the sum of the first 10 elements. So I'll use the reduce function, and what I'll do is I will add each element with the next element, and this should give me the sum of all the elements in this RDD. So when you add up all the elements from 1 to 10, the final result would be 55. Similarly, let's say I create an RDD which would have these string elements Abe, Abby and Apple. Now what I want is in the final result, I would want a concatenation of these three strings as the final RDD. So let's again implement the reduce function on top of this RDD. So here what I'm doing is I am taking each string and concatenating it with each other. So this was our initial RDD which contained three individual strings. We have applied the reduce operation on this and we have got a final string which is a concatenation of these three individual strings. So after this we have the first function. So the first function, as the name states, basically gives us the first element of the RDD. So I'll create an RDD like this which contains these three elements Apple, BT and Beatrice. So I'll apply the first function on top of this names to RDD to get the first element, right? So see that the first element is Apple and that is what we have extracted. And then we have the take function which returns the first n number of elements from the RDD. So over here I create an RDD nums which contains these elements. Now let's say if I wanted only the first four elements. So I'll just type in nums dot take and then the parameter would be 4 since I want the first four elements. So here I see that I have extracted only the first four elements from this entire RDD. And then we have for each partition which basically executes a single function for each partition of the data frame. So let's say I create a Spark RDD with these elements 1 to 9 and each partition would have 3 elements. So 1, 2, 3 would come under first partition, 4, 5, 6 would come under second partition and 7, 8, 9 would come under the third partition. Now what I want is for each of these three individual partitions, I want the sum of the elements, that is 1 plus 2 plus 3 for the first partition, 4 plus 5 plus 6 for the second partition and 7 plus 8 plus 9 for the third partition. And this would be the syntax to do that. So on top of this RDDB, I am applying the for each partition function and I will be printing the sum of all the elements for each individual partition. So I'll hit enter. So we see that when we add 1 plus 2 plus 3 we get 6. When we add 4 plus 5 plus 6 we get 15 and when we add 7 plus 8 plus 9 we get 24. Right, so that was a demo on Spark RDDs. Now let us understand the various components of Spark ecosystem. So let me start with the Spark core component, which is the most vital component of Spark ecosystem. So it is responsible for basic IO functions, scheduling, monitoring and so on. And the entire Spark ecosystem is built on top of it. So now you know how important it is. So as we already saw, Spark supports different deployment modes. It can be deployed through Hadoop via Yarn, Mesos or Spark's own cluster manager. Now let's have a look at Spark's ecosystem library. So the library is composed of Spark SQL, MLlib, GraphX and streaming. So Spark SQL helps us in performing SQL-like queries to process the data. Then we have Spark's machine learning library, which eases the deployment and development of scalable machine learning pipelines like summary statistics, correlation, and feature extraction. And graphics component of Spark helps the data scientists to work with graphs and non-graph sources to achieve flexibility and resilience in graph construction and transformation. Then we have the Spark streaming component, which allows us to perform batch processing and streaming of the data in the applications. And since Spark is polyglot, it can be implemented in Scala, R, Python and Java. However, Scala is the widely used language. And when it comes to storage, we can store data over HDFS, local file system and cloud. It also supports SQL and NoSQL databases. So now let us deep dive into the Spark components. So we'll start with Spark SQL. So Spark SQL is a Spark module for structured data processing. And the code for Spark SQL can be written in Java, Scala, Python or R. And Spark SQL helps to query data from data sources like CSV, JSON, Hive and Cassandra. And we can also seamlessly mix SQL-like queries with Spark programs. So Spark SQL lets us query structured data as a distributed dataset or RDD in Spark with integrated APIs in Python, Scala and Java. Another good thing about Spark SQL is it provides unified data access so we can load and query data from a variety of sources. Schema RDDs provide a single interface for efficiently working with structured data, including Apache Hive tables, Bucket files, and JSON files. Spark SQL also has Hive compatibility, so we can run unmodified Hive queries on existing warehouses. Spark SQL reuses the Hive front end and metastore, giving us full compatibility with existing Hive data queries and UDFs. So we simply have to install it alongside Hive. Another notable point is it provides standard connectivity through JDBC or ODBC. So Spark SQL includes a server mode with industry standard JDBC and ODBC connectivity. And finally, Spark is also scalable. So Spark SQL takes advantage of the RDD model to support mid-query fault tolerance, letting it scale to large jobs too. Now let's have a look at some advantages of Spark SQL. So the execution of queries in Spark SQL is much faster than Hive. So let's say if it takes 600 seconds to execute a query in Hive, it will only take 50 seconds in Spark SQL. And there are no hurdles if you want to migrate the Hive code to Spark SQL. And as we already know, we can do real-time querying with Spark SQL. Now let's look at the Spark SQL architecture. So let's start with the data source API. So this is a universal API for loading and storing structured data. And it has built-in support for Hive, Avro, JSON, JDBC and Parquet. It supports third-party integration through Spark packages and also has support for smart sources. Then we have the data frame API, which is a distributed collection of data in the form of named columns and rows. It is basically equivalent to a relational table in SQL used for storing data in tables. And it is lazily evaluated like Apache Spark transformations and can be accessed through SQL context and Hive context. And the next component is SQL Interpreter and Optimizer. So SQL Interpreter and Optimizer is based on functional programming construct in Scala. It is the newest and most technically evolved component of Spark SQL and provides a general framework for transforming trees, which is used to perform analysis, optimization, planning, and runtime code spawning. It also supports cost-based optimization and rule-based optimization, making queries run much faster than their RDD counterparts. And there is also SQL Service, which is the entry point for working along structured data in Spark. It allows the creation of data frame objects as well as the execution of SQL queries. So now let's learn how to create data frames and work with Spark SQL in Spark. So we'll start off by learning how to create a data frame in Spark. So I'll create a list with these three elements. So the first element has 1 mobile and 50,000, the second element has 2 shoes and 4,500, and the third element is 3 TV and 70,000. Now what I want is to convert this into a data frame where this will be the first row, this will be the second row, and this will be the third row. And to do that, I would have to use the toDF function. So on top of this object which I've just made, product, I will use the toDF function and I will give the names of the three columns. So the name of the first column would be PID, the name of the second column would be product, and the name of the third column would be value. So now let me have a glance at the data frame which I've just created. I will just type out product df dot show. So we have successfully converted this list into a data frame where This became a first row, this became a second row, and this became a third row. Now we'll go ahead and do some basic operations on Spark data frames. So here I am reading a JSON file as a data frame. So the command for that would be spark.read.json, and inside this I will give in the path, which is student1.json, and I will store it in df. So df is a data frame. Now as we had already seen earlier, if you wanted to show the elements or the records inside the data frame, we will use the df.show function. And if we also wanted to see the schema of this data frame, then we'll use the print schema function on this data frame. So df.print schema tells us that this data frame has two columns. First column is age, which is of type long. Second column is name, which is of type string. So now what I'm doing is, with the help of the select function, I am extracting only the name column from the entire data frame. So df.select name. So this data frame actually has two columns, name and age. But if I want to extract only individual columns, then I'll use the select function. So df.select name, and then I'll show it out. So we have extracted only the name column. Now similarly, let's say I wanted to extract only those records where the age of the person is greater than or equal to 18. So for this, the command would be this. So on top of the data frame, I'll use the filter function and specify the condition that age needs to be equal to or greater than 18. So we have 3 records, but out of those 3 records, we get only these 2 because Janet's age is equal to 18 and Serena's age is more than 18. And then in the final command, we are grouping the data frame with respect to the age column, and I want to find the count of number of persons for each age value. So there is one person with age 18, one person with age 17, and one person with age 19. So these were some basic operations on Spark data frames. Now we will go ahead and apply some Spark SQL queries on top of the same data frame. So for that, I would actually have to create a temporary view. Command would be create or replace temp view, and then I will pass in the name of the data frame, which would be student1. So let's go ahead and apply our Spark SQL queries. So in the first command, what I'm doing is I am extracting all the records. So we have a simple SQL query, select star from student1, which gives us all the records from this table. Now similarly, if we wanted only those records where the age is equal to 17, this would be a syntax. So select star from student1 where age equals 17, and this is the result which we get. So now let's understand about Spark's machine learning library, MLlib. So MLlib basically consists of 2 packages. First is spark.mllib, which contains the original API built on top of RDDs, and it is currently in maintenance mode. The second package is SparkML, which provides higher level API built on top of data frames for constructing ML pipelines. And Spark.ml is the primary machine learning API for Spark now. So with the help of MLlib, you can implement statistical analysis, you can implement classification and regression algorithms such as linear regression, naive Bayes, and decision tree. MLlib also supports clustering algorithms such as k-means and Gaussian mixture. So there are multiple things which you can do with MLlib. Now let us implement a demo on MLlib. So let me start off by loading all the requisite packages first. So we will basically be implementing the linear regression algorithm. Now let me load the dataset and show you guys the schema of this dataset. So over here we are loading a CSV file with the name e-commerce customers, and we are storing it into a data frame, and the name of that data frame is ecom.ds. Now after that we have printed the schema. So you see that these are the different columns available in this data frame. So we have email, which is of string type, address, which is of string type again, avatar, which is of string type again, and then we have these double values: average session length, time on app, time on website, length of membership, and yearly amount spent. So we basically want to apply the linear regression algorithm on top of this yearly amount spent column. So this yearly amount spent column would be the dependent variable, and the rest of the double values would be the independent variables. So average session length, time on app, time on website, and length of membership would be the independent variables, and yearly amount spent would be the dependent variable. So now what I'll do is I will go ahead and select only these double values from this entire data frame. So I'll use the select function and I will be selecting this yearly amount spent column as label. So I will name this column as label, and the other columns I'll be selecting the same, and I'll store this result in ecomdf1. After that, I'll use a vector assembler which helps me to take in all of these independent variables and store them in a single column and name that column to be features, right? So this is the syntax. So I'll type new vector assembler and I will first take in all of the input columns, which are nothing but all of the independent variables. So these are all of the independent variables and I will be storing them under one new column and name that column to be equal to features. And I'll store this in an object and name that object to be assembler. So after this, I'll apply this transform function on top of the ecomdf1 data frame. So over here, we are basically creating a data frame which will have just two columns. First is the label column, next is the features column. So this label column would be our dependent variable and this features column has all of the independent variables, and we are storing that in ecomdf2. So now let me just show you guys how the data frame looks like. So I'll type in ecomdf2.show. So this is our final data frame. This is our dependent variable with the name label, and this is our independent variable features, which contains all of the independent variables. So after this, I will go ahead and create a new linear regression object and name that to be LR. So we can create a new linear regression object with the help of this linear regression function. Now after this, we will go ahead and build the linear regression model on top of the ecomdf2 data frame. So the function would be lr.fit and I am storing the result in LR model. So now that we've built the model, let's actually have a look at the training summary. So over here, I will use the summary function on top of the model which we've just built and I'll store it in training summary. And I would want to know the residuals of this training summary. So these residual values are basically the error in prediction, or in other words, the difference between the actual values and the predicted values. So over here, these are all of the residuals for the first 20 rows. Now let's also have a glance at some performance metrics. So we are printing the root mean square error, the mean square error, and the R square value. So we see that the root mean square error value is 9.92, the mean square error value is 98, and the R square value is 0.98. So this was a simple demo on MLlib. Now it's time to understand what is data streaming. So data streaming is a technique for transforming data so that it can be processed as a steady and continuous stream. A data stream is an unbounded sequence of data arriving continuously. Today there are so many users out there using various streaming sources like YouTube, Netflix, Facebook, and Twitter, and all these sources provide live streams of data. Thus, streaming technologies are becoming increasingly important with the growth of internet. So this is where Spark streaming comes in and helps in processing real-time streaming data. Spark streaming also enables high throughput and fault-tolerant stream processing of live data streams. And with Spark streaming, we can perform RDD transformations on mini batches of data. So the fundamental stream unit here is dstream, which is basically a series of RDDs to process the real-time data. Now let's understand the workflow of Spark streaming. So Spark streaming receives live input data streams from various sources. It then divides the data into multiple batches, which are then processed by the Spark engine. And then it generates the final stream of results in batches. So this is the workflow of Spark streaming. Now let's look at the final Spark component, which is graphics. So graphics is an API for graphs and graph parallel computation. So GraphX unifies ETL process, exploratory analysis, and iterative graph computation within a single system. And the use of graphs can be seen in Facebook's friend list, LinkedIn's connection list, link between internet's routers, and also Google Maps, just to name a few. Now let's head to the quiz. So Apache Spark has APIs in which of the following languages? Well, think about it and write down your answers in the comment section. So this brings us to the end of the session. Thank you very much for attending.